Good morning, everyone. Today, I would like to present our research on challenges, pitfalls, and perils of using hardware performance counters for security. This work was done in collaboration with Jan Warner, Manos Antonikakis, Michalis Polychronikis, Fabian Monros. My name is Sanjeev Das. I'm a postdoc in University of North Carolina, Chapel Hill. Modern processors provide a unique ability to visualize hardware-related activities through a special set of registers called hardware performance counters. They are available in processors for more than 2 decades. They are used to monitor and measure hardware events such as instructions, memory accesses, cache hits, misses, translation look-aside buffers, hits and misses. They have been used in many application domains such as software profiling, debugging, high-performance computing, power analysis, and we have seen recent rise in the use of performance counter in security domain. HPCs provide a good foundation for measuring microarchitectural information that are typically not available by any other traditional tools. For example, branch misses, cache misses. Moreover, this information can be obtained at a very low performance overhead. Given these advantages, it's no surprise that it has been used in security applications for various purposes, such as malware detection, rope detection, rootkits development, side channel attacks. We recently saw the talk on Spectre. Even for recent side channel attacks such as Spectre and Meltdown, researchers have looked into how performance can be used to defend these attacks. Given the wide popularity of performance counters, I got an idea. Can we use performance counters to defeat data-only attacks? Joining the new research who had the good experience on data-only attacks, and since I had some good experience working on performance counter, I thought it would be a quick win for me. We can quickly write a paper and impress the group. Working on this idea, we encountered several challenges. There are hundreds of performance counter events. Understanding microarchitectural interaction is a daunting task, and more of these events are related to one another. So the bigger question was, which events should we choose to model the data-only attacks? Moreover, there are many different frameworks built using hardware performance counters, and the collection techniques varies across these frameworks. So another question raised is there a standard way to collect performance counter measurement? After spending weeks on these challenges, we encountered more substantial problems. We found the seminal work by Weaver and McKee, which highlighted the non-determinism issues in performance counter. Measurement given by performance counter varies across different runs. Non-determinism issues drove us crazy. We are baffled. On top, there is lack of application level profiling of performance counter data at the hardware level. I felt to be on the edge of the cliff. A quick win idea turned out to be Herculean task. We thought of it, and we realized these issues cannot go unnoticed. These pitfalls must have been encountered by other researchers as well. Thus, we started looking into the literature, and we wanted to understand if they have been addressed, how can we use them in our approach. Therefore, after spending 2 months full-time into the literature survey, we analyzed around 100 papers from different application domains such as debugging, power analysis, performance analysis, and security. To supplement our understanding of how performance counters can be used by different approaches, we sent questionnaire to the authors, even though response turnout was not very high. Of these 100 papers, 56 papers were those papers that specifically acknowledged the non-determinism issue. They were mostly from non-security application domains, which initially were the users of hardware performance counter. Quite surprisingly, we found that 45% of these papers did have reservation of using performance counters. They do not recommend using performance counter because of two reasons. One, lack of determinism in the performance counter, and two, lack of portability of performance counter events across different microarchitecture. Some events could be present in one microarchitecture but may not be available in another architecture. Thus, my initial idea of using a hardware performance counter for data-only attacks defense was doomed. Next, we look into 40 security papers that has recently used HPCs. We found that only 10% of them acknowledge non-determinism issues. Some of them argued that their approaches are not affected by non-determinism. It made us constantly go back and rethink whether hardware performance can be trusted, which was the initial issue raised by Weber and McKee 10 years earlier. Going through the literature survey, we found two common failures that has been followed by many security approaches. One, mishandling of performance counter data. This mainly occurs because of lack of process level filtering at the hardware level. And the other main issue was ignoring non-determinism issues. Non-determinism mostly occurs because of two reasons: SCID and over or undercounting of the events. To understand these issues in detail, let us walk through how performance counter data is collected from the hardware. There are a limited number of programmable counters that can be configured to a specific set of events. The configuration is done in the kernel mode. There are two modes to read the counter data: polling and sampling. In polling mode, one can read the counter data at any given point of time. For sampling mode, a specific interrupt is provided by the performance monitoring subsystem called performance monitoring interrupt. It can be configured to trigger the interrupt after n occurrence of an event. As one would expect, first the event has to be configured in the sample mode, such as after n instruction retired. As the program begins execution, after n instructions, the performance monitoring interrupt is generated. At this point of time, all the counter values can be read. Now we look into how performance counter data has been mishandled by many approaches. As discussed earlier, this is mainly because of lack of process level filtering at the hardware level. Many approaches take a shortcut and try to filter the process at the interrupt level. To demonstrate that, let's say a process A executes, an interrupt is triggered. At the interrupt, one can observe whether this belongs to process A or not, using process ID, etc. However, after context switch, there is another process that comes into execution. And again, one can observe whether the current process is process A or not. However, there is a problem. Once we identify that this is not process A, we may disregard that counter data, and this can lead to a loss of events from process A. Similarly, when the process A resumes execution at context switch, and we observe whether a current process is process A or not, we might incorporate noise from process B. However, there is an easy fix. One can save the performance counter data at the context switch and can restore the performance counter data before process A resumes execution. But many papers did not follow this small fix. And this is especially harder in some of these operating systems, such as Windows operating system, which is closed source and it requires changes in the kernel which might not be trivial. Another main issue in performance counter is the skid. Skid is the most frustrating issue and most difficult to deal with. It occurs in the sampling mode. The PMI is not delivered at the time it is raised. There is a late delivery of the interrupt, which leads to variation in the measurements. For example, let's say sampling is configured to be done at every n DTLB misses. However, the PMI is delivered at n plus 10 or n plus 30. This leads to a skid, and this typically affects certain applications such as data-only attacks. For example, this may be because the signature lies in a small code segment. In addition to skid, non-determinism may occur due to other reasons. To dig further into non-determinism issues, we revisited the work done by Weaver et al. We performed the empirical analysis using their benchmarks. We added some new benchmarks. We found that some issues has been fixed in the newer processes. However, some issues still persist. We also found that there are some new issues. Pitfalls. Pitfall leads to overcounting of instructions. After working on several papers, I got buried into the pitfalls. Why do these issues matter for security perspective? An improper usage of performance counter in security application can be disastrous. For example, incorrect data collection can lead to a incorrectness of the approach. Similarly, an advanced adversary can use the non-determinism, and for example, they can trigger pitfalls to undermine the defenses. To demonstrate that, we saw a case study on malware detection, malware classification. We selected the state-of-the-art approach proposed by Tang et al. Following their approach, we sample events every n instruction retired, and we try to see how incorrect data handling can lead to an incorrectness of the approach. We perform multi-class classification using machine learning approach. We found that incorrect data collection can impact detection accuracy. For certain malware families, the discrepancy between the two discrepancy is almost more than 30%. In some of the cases, even handling data correctly doesn't have a higher accuracy. This begs a question: are HPCs a good foundation for malware detection? We refer the audience to the concurrent work done by Zhou et al., which was published in ACS-CCS. However, the title speaks for itself. We also perform another case study on rope detection. For detecting return-oriented programming attacks, Wang and Baker propose a state-of-the-art approach where the basic idea is that the rope attacks have higher number of return instruction per total instructions executed, which allows us to set a threshold value such that these attacks can be detected. Besides, the rope attack also incur a lot of return misses within a small section of the code. To demonstrate that, let's say we have two performance counters, instructions and return. Rope gadgets executes in the chain, and we can observe that just for 6 return instructions, the total number of instructions is less than, say, only 16. This helps to figure out the rope attack. Now we demonstrate that an advanced adversary can trigger the page faults by embedding manipulator gadgets inside the rope chain and can bypass the detection. The point to be noted here is that irrespective of the parameter choices, page faults can still be leveraged to bypass such detection. For more technical details, we refer the audience to our paper. In conclusion, performance counters offer a powerful capability. However, devils is in the detail. We cannot blindly apply performance counter for critical applications such as security defenses. One has to take care of correct way of handling performance counter data and issues such as non-determinism. To guide the future work on this, on performance counter, we provide recommendations to correctly use performance counter in our paper. Thank you for listening our talk. Any questions?
If you have questions, come to the center. Remember, state your name and affiliation, please.
Hello, my name is Erica Leal. I'm from the University of Texas at Arlington. Using your recommendations to use HPCs regarding security, where do you see the future of that?
So it depends. For critical applications, such as security defenses, we cannot allow more inaccuracies. So for tolerating those noises because of the non-determinism or incorrect non-determinism effects, it would be very hard to implement that. It would be not good for those defense mechanisms because those can impact the accuracy of the approach. Whereas if an approach can tolerate the non-determinism effects, and if the data can be handled correctly at the context switches and all, then I think those applications can be using security, can be using performance counter.
So I have a question. So, you know, as we're going to find out next with the eviction set talk, sometimes what's good for defenses are also good for attacks. Namely, if I have a fine-grained notion of time or events, that may be good for having a low-cost defense that uses hardware primitives, but it also might be good for attacks that want to create a side channel or covert channel. What are your feelings about this trade space?
Yes, I think since attacks needs to be done only once, the success rate can be low in attacks. I think one can use attacks, a performance counter for attacks. That would be more beneficial for the advanced adversary. However, for the defense, where we need to have a high accuracy, we cannot allow the defense mechanism to break because of the manipulation of the events. I would suggest it's better for the attack mechanism.
Great, thank you, Sanjeev. Everybody thank our speaker.